So last time we described how the spectrum of the cohomology ring is related to the set of thick subcategories of the small stable module category and the localizing subcategories of the big stable module category. So let me just remind you how that statement went. So H star of G comma K, we take the projectivized spectrum, namely the homogeneous prime ideals in there, except the maximal one. So let's give that a name. Let's call that sort of script V. Then the thick tensor ideal subcategories of the small stable module category are in 1-1 correspondence with specialization closed subsets of this V. And this is really a statement that the Balmer spectrum of the small stable module category is precisely this set. And the topology of this is exactly the Zariski topology. And the localizing localizing tensor ideals in the big stable module category are in 1-to-1 correspondence with all subsets of V. And this correspondence, you can think of it as being given in two ways. One of them is the support, the cohomological support, and the other was the pi support. And they give the same answer. And the interesting feature of that is that each description gives you a number of properties that are not really terribly visible through the other description. In particular, the pi support is what tells you that the points in V really correspond to minimal localizing subcategories. So it's really essential as part of understanding this classification. Now, you'll notice that what I...
So these weren't proved without pi support?
These weren't proved without pi support. Yeah. But you'll notice that there was one prime ideal missing here, and the first thing I want to do today is to put it back. And for this purpose, I want to introduce a slightly bigger category than the stable module category that has just one more point in its Balmer spectrum. So I'm going to talk about K inj of Kg. And this is going to be closely related with the cochains on the classifying space. So, there's a relationship between the stable module category and the cochains on the classifying space, but this is more closely related to the cochains on the classifying space. In fact, when G is a finite P group, this will be exactly equivalent to the derived category of the cochains on the classifying space. So what is this category? Well, its objects are complexes of injective, and remember that's equivalent to projective, kg module. Kg module. And the arrows are homotopy classes of degree 0 chain maps. So this is a triangulated category in the usual way. The triangles are formed by taking cones of maps of complexes and so on. And the shift is just the shift in degree of a chain complex. So this is a triangulated category. And how does the stable module category sit in there? Well, you remember in the first lecture I told you what a tape resolution was. The tape resolution of a module is an exact complex of projectives where the image of the middle map is your module. So it's an object in this category. So if I think of the big stable module category of Kg is really equivalent to the homotopy category of acyclic complexes of injectives. Passing down to the homotopy category actually is exactly what kills the projective maps. So that sits inside, oops, I'm screwing up the notation here, sorry, acyclic inj of Kg. And this sits inside of K inj of Kg. And what happens when I take the Verdier quotient? Well, I'm just passing down to the derived category. This is the big derived category of all unbounded complexes of all. Well, yeah. Yes, I mean, yeah, so it's done through semi-injective resolutions, yeah. And both these functors have both a left and a right adjoint. So we have a recoulement of tensor triangulated categories. The tensor identity here is the injective resolution of the trivial module. And the tensor identity here is the Tate resolution of the trivial module. So they're actually different tensor identities, but you kind of have to cope with that. So what about the compact objects in here? Not all of these arrows preserve compact objects, really. So the compact objects in the derived category are the perfect complexes of Kg modulus. So it's the bounded in both directions exact sequences of finitely generated projectives, the perfect complexes. Here, actually, the compact objects are the semi-injective resolutions of things in the bounded derived category of Kg. And only the left adjoints preserve compacts. And what is the quotient then of dB of Kg by perf of Kg? Well, Rickard's theorem says that's actually a copy of the small stable module category. So this is sort of, I mean, these are the right categories for when you take the small version, getting this relation. And what do I want to say about that? Yes. Oh, so I wanted to tell you what this says about thick subcategories and localizing subcategories. Well, so inside the perfect complexes, there are actually no proper tensor ideals. So this is like, from the Balmer point of view, this is a point. And its support is exactly that maximal ideal. And so what we're doing is we're taking the proj of the cohomology ring and gluing in a closed point that's in the closure of everything. So it's the only closed point. So the Balmer spectrum in dB of kg is actually proj of h star of gk union just a single point, the maximal ideal, and the closed sets are the closed sets in here union that together with the empty set. And so you get a theorem exactly like this for the bounded derived category, but you have to enlarge V by taking the union with this extra point. Okay? Yeah, so I won't write down the classification theorem, but if you just replace the small and big stable module categories by the bounded derived categories and k-inch, and you replace V by V union this extra point, it's the same theorem. And, okay, so are there any questions about that before I move on? Yes?
So just to get that clear, when you say is there basically two ways to get to triangulated category, which is what we do is dB, and what we do is our stable module category, and you're comparing the spectrum, and you say only one point more than the other.
Yes. Yeah. So this has a single point as its Balmer spectrum. This has this V, and this is just the two glued together. Now, what's the question?
It's a nitpicking. The perf kg does not have a unit because k is not in there. So it's just an ideal in dB. So it's just its support as a point.
Yes, exactly. This doesn't really have a Balmer spectrum in the literal sense, but it's an ideal supported at that point. Yes, thank you. So, on the other hand, let's have a look at cochains on BG with coefficients in K, which I'm just going to shorthand to cochains on BG. This, I mean, there are various ways of looking at this. Let's look at it as a differential graded augmented algebra. And let's have a look at the category D of cochains on BG, the derived category. So the objects are the differential graded modules, and the arrows, well, you do those in two steps. You take the the homotopy classes of maps of chain maps, but then you invert the quasi-isomorphisms. You just adjoin formal inverses to the quasi-isomorphisms, the things that induce the identity, or sorry, induce an isomorphism on cohomology. And so, what's the connection between this and K inch of Kg? Well, in K inch of Kg, the endomorphism differential graded algebra of this tensor identity, this is end Kg on it, I suppose. So think of this as a differential graded algebra of just homomorphisms of various degrees from that resolution to itself. This is, as a differential graded algebra, it's equivalent to cochains on BG. Now, what that implies is that you can think of this derived category. Well, there's a slight problem, which is that IK doesn't necessarily generate that category. If it did, and that's the case when the group is a finite P group, so if G is a finite P group, then IK generates K inch of Kg. So that induces for you an equivalence between K inch of Kg and the derived category of this differential graded algebra and Kg of IK. And then because of this equivalence, that's equivalent to the derived category of cochains on BG. So somehow cochains on BG is like a causal dual of Kg in the case of a P group. And actually, in the case of a P group, you can get back the group algebra Kg by doing this again. You take the trivial module over cochains on BG and take its derived endomorphism ring, and you get back something that's quasi-isomorphic to Kg. So actually you've got these two causal dual differential graded algebras with equivalent derived categories. And so that's really the relationship between this slight enlargement of the stable module category and the derived category of cochains on BG. For a finite P group, they're causal dual. But not all finite groups are P groups, and something very interesting happens when the group is not a P group. In that case, you still get functors, but you don't get a causal duality. If you dualize twice, you get to something interesting that we hadn't seen before. Okay, so if G is a general finite group, so what happens? Well, all that end of IK sees is the localizing subcategory of K inch generated by IK. So if I take the localizing subcategory generated by IK, there's a subcategory of K-inj of Kg. That's quite an interesting subcategory. And that is then equivalent to the derived category of end Kg, this differential gradient algebra. And then we can still do the further equivalence to cochains, sorry, derived category of cochains on Bg. Okay? But when we try and go back again, we fail. And what this has to do with is what happens when you try and run an Eilenberg-Moore spectral sequence. Okay? So, let's say something about the Eilenberg-Moore spectral sequence. If you've studied the Eilenberg-Moore spectral sequence, you'll probably know that it works well for nilpotent spaces, but doesn't really work terribly well outside of that. Okay? And so, let's say X is a connected, what do I need? Connected nilpotent, well, let's say a connected space with pi 1 of X, finite nilpotent, just to be really safe. And acts nilpotently on pi I of X, the I bigger than 1. That's plenty enough to make it work, isn't it? Yeah, good. Then you get, well, what I should really write down is cotor over H star X. I should probably put it under H star of X. Does that look right? K converges to H star loop space on X. Is that accurate?
You could use homology.
Sorry?
That should be homology.
This?
I wanted it.
If you did,
I've done cotor over cohomology converging to homology. Is that right? No.
I think you want X on cover. If you had X, that would be.
That's excellent. That's really what I wanted to say. So let's erase cotor and write X. Are we happy then?
Then you'll have to also erase the upper. We're going to want the H star as a subscript.
Excellent, good. X star H. Oh, I see. Yes, I'm dualizing everything. Yes. Sorry. Yes. Yeah. So this is really the dual of the Eilenberg-Moore with cotor over H lower star. Yes. Sorry. Okay, so we have a spectral sequence like this. Now, Bg is not nilpotent here, but I can sort of force it to be nilpotent. If back in the case where G was a finite P group, Bg was nilpotent, and loops on Bg was just equivalent to G, which is why we got back sort of H star of G as a discrete set is really just the group algebra. But here, I'm going to have to get rid of some part of BG in order to make the Eilenberg-Moore work. And how do we do that? Well, that is Ausfeld-Kahn P-completion. That's how you force a space to have nilpotent fundamental group without changing its homology. So if X has finite pi 1, then Ausfeld-Kahn P-completion, finite pi 1 ensures that the space is P good in Ausfeld-Kahn's terminology. And then the Ausfeld-Kahn P-completion has nilpotent pi 1. In fact, it's the largest P group that's a quotient of that pi 1. So it's what we write as pi 1 of x modulo O upper P pi 1 of x. O upper P is just the smallest subgroup where the quotient is a P group. And is homologically equivalent. So in fact, the chains or cochains on X are with FP coefficients, say, is equivalent as a differential graded algebra, quasi-isomorphic to cochains on X P completed, which I'm going to write like that, FP. So if I try and run the Eilenberg-Moore spectral sequence starting with the cohomology of BG, what I'm going to do is I'm going to converge not to the homology of the loop space on BG, but to the homology of the loop space on its P completion. Okay, so I get a spectral sequence going from X star star H star P G. Everything's with coefficients in a field of characteristic P here. K, K converges to H star of loops on not BG, but now BG P completed.
Don't you need also the BG to be completed?
Do I need what?
In the X also the BG to be completed?
Makes no difference.
X over H star of BG.
Oh, H star BG is the same as H star of BG P completed.
Oh, cool.
Yeah. Yeah, so suddenly if I try and run the Eilenberg-Moore, I pick up a P completion, is really what I'm trying to say. And this is a derived statement, this is a shadow of a derived isomorphism, which is really saying that the endomorphism differential graded algebra of K over cochains on BG is equivalent to chains on the loops on BGP completed. So when I try and do this causal duality, well, the first stage, I lose everything that's orthogonal to IK when I move over to cochains on BG. But at the second stage, what I get back is not actually KG, but I get chains on loops on BGP completed. So what I end up with is equivalences between log of IK contained in K inj of KG the bounded derived category, the full derived category of cochains on BG, and then you get the full derived category of the chains on the loops on BGP completed. So this is somehow a causal double dual of the group algebra. So, I mean, think about it this way. Think about what happened if you started with a finite group with no normal subgroup of index P. Okay, so you built BG, you then P completed, which completely gets rid of the fundamental group, but doesn't change the homology. And then you try and get back the fundamental group, but instead you pick up this. Okay, and if you try and compute what this, what the homology of this is, it's actually quite closely related to the group algebra of KG, except that there are kind of, I mean, there are differences in the way it looks, and it's actually quite sort of disturbing. But you know, the way I think of it is that this is a sort of proxy for KG. So let me give you, I suppose I should give you an example, shouldn't I? I should warn you that I sort of didn't really carefully plan out what I was going to say today, so this is sort of stream of consciousness, but you probably already gathered that. So, an example. So let's choose something that is, well, what's the smallest group we can think of that's not penile-potent, let's say? Symmetric group of degree 3 and characteristic 3, does that do it? So G equals the symmetric group of degree 3, characteristic of K is 3. So this is really the dihedral group of order 6, if you like. So it has this normal subgroup of order 3, and the cohomology is just the invariance of the cyclic group of order 2 on that cohomology. So H star B sigma 3 is, well, it's got, let's see, what do I want to call these generators? Probably X and Y? T, thank you. Thank you, John, co-author. Where the degree of X, I'm not going to use John's homological grading, so I'm going to call this 4, not -4. The degree of T is 3. Okay? So you sit and run an Eilenberg-Moore on that, and then you ungrade it, and what you find is that the homology of the loop space three completed is, well, I have two generators which I could call psi and tau for reasons that they're dual to x and t. So the degree of psi is, well, it's homological degree 3. Don't get confused by the fact that these are cohomological degrees and these are homological degrees. And the degree of tau is 2, and there's a single relation that says psi squared and tau cubed are the same. And the strange thing in this case is that actually this algebra is formal as a differential graded algebra. It's equivalent to its homology. So the derived category of this thing is actually the derived category of its homology, considered as a differential graded algebra with differential 0. So you can actually write down what the modules look like. I should warn you that this is a bit misleading, because it's the only case where you don't get an exterior generator when you try and start off with something with a cyclic Celoff P subgroup. So John and I worked out what happens for anything with a cyclic Celoff subgroup. Yes?
Are they usually commutative?
Sorry?
Are they usually commutative like that?
No, so this is not commutative. I should warn you about that. If it were commutative, then a degree 3 generator would square to 0.
You mean? Okay, so you put.
We're in characteristic 3. So commutative says that psi times psi is minus psi times psi. Psi. And so psi would have to square to 0. And it doesn't. It squares to tau cubed. And there's no reason why these should be graded commutative at all. And in fact, there are much more non-commutative examples. I should probably mention the dichotomy here. So, so this is due to Ranlevy. H star of the loops on BG P completed is either of polynomial growth in other words, just the growth is bounded by some polynomial in the degree, or at least semi-exponential growth. And what does semi-exponential mean? It means a constant times e to the some other constant times square root of n. So if you add up the first n dimensions, you get at least this. We don't actually know of anything of semi-exponential but not exponential growth. And I should give you an example of something with exponential growth. So if you take an elementary abelian group of rank 2 with p at least 3, and take a semi-direct product with a cyclic group of order 2 that is just inverting everything, just sending each element here to its inverse when you conjugate. This group, well, once I decompute its classifying space, I'll get trivial fundamental group because this has no p groups as quotients, but actually the loops on the classifying space, the homology grows exponentially. So after a while, each dimension is just like approximately p times the previous one. So this has exponential growth, but it's, it has exponential growth in quite an interesting way. It's still finitely generated, but it's sufficiently non-commutative that it manages to have exponential growth. And in fact, there's a free subalgebra over which it's a finite module. So I mean, there are various conjectures that you might make at this point that, for example, in the case of polynomial growth, in the examples we know, there's always a central finitely generated commutative subring over which it's finite as a module. And in the semi-exponential case, you might guess that there's always a free subalgebra there, so that would explain the exponential growth. We don't know whether any of those statements are true. One might even guess that always the homology is finitely generated as an algebra. We're certainly very far from knowing whether that's true. So I mean, there are some very interesting, just finite dimensional commutative rings constructed by David Anick, where if you take x over that ring, you get semi-exponential growth that isn't exponential. So it can't be finitely generated. And actually, I mean, the way to think of this is it's roughly the way that the partition function grows. And David Anick's examples all look like the partition function somehow.
In your examples, do you see some split based on the size of the PCL subgroup or anything like that?
No, it's really weird. So, I mean, if you just go down to a subgroup of index 2 here, it becomes a polynomial graph. Well, it becomes the group algebra, which is of zero growth. So, I mean, there are examples of two groups with p-primed index, where one is exponential and the other is polynomial in both directions. So it's a really subtle invariance of the space or of the group. And I think it's fair to say that we don't understand it, but it seems to be connected with notions of derived complete intersection for this ring, or for cochains on BG. Okay. Oh yes, this is where I'm supposed to hum to myself, isn't it? So I do have time to tell you about some conjectures a conjecture that John Greenlee's communicated to me that I think is very interesting about the bounded derived category of cochains on BG. So I mean, if you look at this correspondence between K inch of kg and cochains on BG, you may wonder what the small versions are looking like. So the small version of K inch was just the bounded derived category. So what is the right small version of the derived category of cochains on BG? So let's make a definition. I think it's fair to say that it's not 100% clear that this is the right definition, but let's make it anyway. The bounded derived category of cochains on BG is the full subcategory of D of cochains on BG, consisting of objects X with cohomology of X, just as complexes, finitely generated as a module over cohomology of BG. Okay? So inside that, you might think of the perfect complexes as the thick subcategory generated by the ring cochains on BG. Yeah. But these sort of seem like reasonable definitions, and then you might write the singularity category for the Verdier quotient. So just take dB cochains on BG and mod out by the perfect complexes. So what does this look like? Well, we sat and calculated it in various cases. The easiest case is if G is a finite P group, then D singularity cochains on BG is the zero category. So somehow, finite P groups, the cochain is a regular ring in that sense. Okay, remember, regular ring is exactly something whose singularity category is zero. And in general, if you make the same construction with just an ordinary commutative Noetherian ring, what is the singularity category? Well, what you should get is something whose support is exactly the singular set of the corresponding variety. So somehow this statement that the cochains on B of a finite P group, the singularity category is zero, that's the statement that cochains, the singular set is just zero. So if G has cyclic Celoff subgroups, by the way, I should probably have mentioned Greg Stevenson at some point in setting up with John Greenlee's this causal duality which I was talking about. Is that accurate?
Yes.
Yes, good.
I think you should also say that we did make a decent case that this is a good definition.
Okay, good.
It may not be the only definition.
It may not be the only definition, but it's a good definition. There you go. If G has cyclic Celoff P subgroups, is it 4 o'clock?
Yes.
Yes, good. If G has cyclic Celoff subgroups, then D singularity cochains on BG is a Kroll-Schmidt category with only finitely many isomorphism classes of indecomposables. Now, you shouldn't be misled by this. The number of isomorphism classes of indecomposables, we know how many there are. It has nothing to do with the number of isomorphism classes of indecomposables in the stable module category, which is also finite. Okay? I've also sat down and calculated a bunch of other cases in characteristic 2. There's one case that somewhat surprised me, where if G has semi-dihedral Celoff 2 subgroup, so that's generated by x and y such that x to the 2 to the n is 1, y squared is 1, and yxy inverse, which is the same as yxy, is just x to the 2 to the n minus 1 minus 1. So you send it just less than halfway around the cycle, and has no subgroup of index 2, For example, the sporadic Matteo group M11, then cochains on BG with F2 coefficients is actually formal. It's a really strange statement. So usually cochains on BG is very far from formal. The only cases where it's clear that they're formal is when P is 2 and the Celof 2 subgroup is elementary abelian. Apart from that, there are some sort of sporadic examples like that, but I don't understand why they're formal. I just know that they're formal. I have never seen at an odd prime a formal cochains on BG, but I can't prove that they don't happen. But what I want to write down is a conjecture which was communicated to me by Greenlees, that cochains, if P is a Celof P subgroup of G, then cochains on BP is a module over the cochains on BG via restriction. The conjecture is that this generates the bounded derived category of cochains on BG. If this is true, there are loads of consequences, and we can really describe this bounded derived category just representation theoretically. And then describe the singularity category. I should also mention what the co-singularity category is. Instead of modding out the perfect complexes, you mod out what's generated by the residue field, which is a bit like passing down to sheaves. So in this cyclic Celof subgroups case, the co-singularity category is also a category of the same type, but has a different number of indecomposables. So we've been trying to prove this conjecture or find a counterexample for the last, 7 or 8 months, and failing in both directions. So if anyone can provide us with some proof or counterexample, we would be extremely grateful for that. I think probably this is a good place to start, actually. Oh, apart from one comment, which is that I have a good guess as to what the singular set is for an arbitrary finite group. It's something called the nucleus, which comes up in representation theory.
Thank you. Other questions?
Stunned silent.
Do you have calculations for that in any of the examples?
Yes, so it's true for cyclic and the tame ones where I've been able to actually compute.
So you said that the conjecture would imply some statements that are of representation theoretic nature. Could you give us a flavor of that?
Well, I believe that an equivalent statement to this is actually that if M is a KG module, I haven't checked the details of the equivalence, but I believe that it's saying that if M is a KG module and cohomology of G, M is finitely generated as a module over the cohomology ring, then there are maps M to M prime, M double prime, where these are cohomology equivalences, and M double prime is finitely generated. So, I mean, it may not just take one map, but I think 2 maps is enough. So that, I mean, this might look more natural, but I still don't know why it should be true.
Did you want me to put that up a bit?
So if it's not the case, let's thank the speaker again for the